Well, relationships involving heat of reaction. So if we have this chemical reaction, carbon plus oxygen to give carbon dioxide, and the heat of reaction is this number. If we use twice as much carbon, so this amount of energy is for 1 mole of carbon. If we double the coefficients and we do 2 moles of carbon, then it seems reasonable, at least to me, that we would get twice as much energy. Does that make sense? You burn twice as much wood, you get twice as much energy. So if we double the coefficients, we double the heat of reaction. If we take this chemical reaction and we make it go the opposite direction, instead of forming carbon dioxide, we're decomposing carbon dioxide. Well, instead of releasing energy, now that's going to absorb energy. Energy cannot be created or destroyed. And so we can't just be able to make a reaction go back and forth and have energy either be created or destroyed. It has to be the same amount. So you change the direction of the reaction, you just change the sign on delta H. And then if we can take that reaction and express it as a series of steps, then the overall heat of reaction is just the sum of the steps. So let's go to an analogy first. So here I have some sort of a podium, right? And let's say that this difference here is 4 feet. And this step is 2 feet, and that's 1 foot and 1 foot. So difference in elevation is a state function, doesn't matter how you got there. So if you're down here on the ground and you're going to the top, you're going to have a change in potential energy, a change in elevation corresponding to 4 feet. Does it matter if I jump from the ground up here or if I go up the stairs? No, my change in elevation is the same. So if I go up the stairs, I've got 1 foot plus 1 foot plus 2 feet. And if I just go directly from the ground to the top, I have 4 feet. The sum of the individual steps equals the overall change. Everybody okay with that? That's what we're talking about with the change in energy of different reactions. And this is called Hess's law. The change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So here I have A plus B going to C. So I can do that directly. No. This is confusing even to me. That's not good. Okay, so what I'm doing here is I'm looking at A plus 2B going to 2D. That's the overall reaction. But I could do that in a different way. Instead of going from this line straight down to this line, I could go A plus 2B makes C, and then C decomposes and makes 2D. It's like going up these stairs instead of just leaping. So I can take the change in enthalpy for this step and the change in enthalpy for that step and add them together, and they will equal this step here. Okay? It's just here I'm going up and coming back down instead of just going down. Does that make any sense? I didn't do that very well. Hopefully it'll go better tomorrow. The reason that it's important that enthalpy is a state function is that we can use that Hess's law to find enthalpy changes for reactions that we can't measure by looking at the steps. So if we have this overall reaction, we want to know delta H for this reaction. We have this information. We have these other reactions where someone else has already measured the enthalpy change. What we need to do is we need to find a combination of these that will add up to this reaction. So let me go back a minute. So what we're doing over here, our overall reaction was A, yeah, it really helps to select a pen, A plus 2B making 2D. So that was going from this line to this line. We also had A plus 2B going to C, and then C going to 2D. So let's think about this. A reacts with B and forms C, and then C reacts and forms 2D. Is there any C left? No. It got made and then it got used up. So what we can do with chemical equations is similar to what we can do with mathematical equations, and we can add these and say that the C here got used up here, so it went away. It was formed and destroyed, so it's not there anymore at the end. And what do we have left? We've got A plus 2B goes to 2D. So that's what we're going to try to do. It's easier with the letters than with the chemical formulas. So we're looking for a combination of these that will add up to this. And exactly how you go about this just depends on how your brain works. The nice thing is you'll be given problems where you have a limited number of choices, and there is a solution within the combination of these three equations. In actuality, the CRC has pages of equations like this and heats of reactions. And so if you're not handed a nice problem, then you've got way too many choices and it becomes more difficult. But we're not going to have to do that. So how do you approach this? Well, I want to find things that have these reactants. I want to put those on the left side and these on the products. None of these match up exactly. Well, let's start at the top. This one has NO as a product. Over here I have NO as a reactant. So what I could do with this one is I could write it backwards. And this one has NO2 as a product, this one has NO2 as a reactant. So I can reverse the direction of that equation. So I'm just going to write it backwards. 2NO2 gas going to 2NO gas plus O2 gas. I just reversed the direction. What do I have to do with delta H when I change the direction? I have to change the sign. And I'm going to use positives here just to emphasize the sign, not strictly necessary. So instead of negative 113, it's positive 113. Okay, so now I've got one of my products and one of my reactants correct, but I don't want O2 to show up in the end. So I need something that's going to have O2 as a reactant. So let's look. Oh, this one has O2 as a reactant. And it's got NO as a product, so that might be nice. I'll toss that guy in there. In the forward direction. So N2 gas plus O2 gas forming 2NO gas. And delta H for that one is plus 182.6 kilojoules. So here I've got oxygen being formed and an equal amount, 1 mole and 1 mole of oxygen being destroyed. So that's okay. But now I've got nitrogen in here. There's no N2 up here. And what am I missing? I'm missing this one, right? So I'm going to need this equation to help me get rid of the N2. So I have N2 here that I don't want. This one has N2 as a product, so that'll help me get rid of that. Kind of helps if you line up the arrows a little bit so that you can see what's on the reactant and product side. It also helps if you copy it down correctly. Okay, so let's look at this now. This oxygen and that oxygen would cancel each other out. And now I've got this oxygen over here. So I've got two oxygens on this side and only one on that side. What I can do is I can multiply all the coefficients in this equation. So I'm gonna multiply those. I'm gonna take two of these and two of those and make this 4. And when I do that, I have to multiply delta H by 2 also, because if I'm using twice as much stuff, the energy change is going to be twice as big. Well, let's see now. So I've got 2 moles of oxygen over there and 2 moles of oxygen over there. They cancel out. The 2 moles of oxygen that were formed got used up in this reaction. Let's see how everything else is working out. Here I've got 2 N2 and 2 N2s. So I've got 2 moles of nitrogen being formed and 2 moles of nitrogen being used up. So those are not present at the end either. So now I've got NO2 and N2O. N2O, NO2, that's good. And here I have NO and NO, and I've got NO. So I've got my reactants and products correct. My coefficients are a little off, but I'm not going to worry about that just yet. Okay, now I need more space because I took up too much space. So what I'm going to do, I need to erase this part too. I'm going to add these together, and I'm sorry, I'm adding upside down. So add all those together. I've got 2 N2O, that's this guy down here, plus 2 NO2, and over here I have 2 NO and 4 NO, that's 6 NO. That's 6 no's, 1 for each child. No, 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 no. Any questions about how I got that equation, the chemical equation? It's a bit much to absorb. When I add these equations together, these steps, Hess's law says that the change in enthalpy for this overall reaction is just the sum of these. So here I've got the 182.6 times 2 plus this and plus that. So 113.1 plus 182.6 times 2 plus negative 163.2 equals. So delta H equals 315.1 kilojoules, and that's positive. But I was asked to find delta H for this equation. How can I make this chemical equation into that chemical equation? Divide by 2. So if I divide all these coefficients by 2, then this is 1, and this is 1, and this is 3. Now my coefficients are correct. I also need to divide delta H by 2. So delta H for this reaction is going to be 157.55 kilojoules. In terms of significant figures here, this is essentially adding, and so we should have one decimal place. So we're going to call this 157.6 kilojoules. Any questions? Yes? Why did I divide by 2? That's a good question. So when I added all of these together, I had coefficients of 2, 2, and 6. But the actual reaction I wanted was 1, 1, and 3. So I divided the coefficients to make them the lowest ratio. Whatever you do to these coefficients, you have to do to delta H. If you multiply by 2, you multiply by 2. If you divide by 2, you divide by 2. Any other questions?